Welcome to our deep dive into hybridization in chemistry. To kick things off, let's clarify what hybridization actually means. In simple terms, hybridization is a concept that explains how atomic orbitals mix to form new equivalent orbitals, which are then used to form chemical bonds. This idea helps us understand the shapes and bonding patterns of molecules, which can't always be explained by simple electron configuration. Hybridization is especially important in organic chemistry, where it helps explain the geometry of molecules like methane, ethene, and ethyne. As we move forward, we'll see how this concept revolutionized our understanding of molecular structure. The concept of hybridization was first introduced by Linus Pauling in the 1930s. Before this, scientists struggled to explain certain molecular shapes using only the classical atomic orbital theory. Pauling's insight was that atomic orbitals could mix or hybridize to form new orbitals that better match the observed shapes of molecules. This breakthrough allowed chemists to predict and explain the geometry of countless compounds. Understanding this historical context helps us appreciate why hybridization became such a fundamental idea in modern chemistry. Before we dive deeper, let's quickly recap atomic orbitals. Atoms have regions around their nuclei where electrons are likely to be found, called orbitals. The most common types are sp²d and f orbitals. Each has a unique shape and energy level. For example, s orbitals are spherical while p orbitals are dumbbell-shaped. These orbitals play a crucial role in bonding as they are the starting point for hybridization. Understanding their basic properties sets the stage for grasping how and why hybridization occurs. You might wonder, why do atoms hybridize their orbitals at all? The answer lies in the need for stability and optimal bonding. When atoms form molecules, they often adopt shapes that maximize the distance between electron pairs, minimizing repulsion. Hybridization allows atoms to rearrange their orbitals into new shapes that better suit these needs, resulting in more stable and predictable molecular structures. This process is especially important in carbon-based molecules, which we'll explore in detail soon. Hybridization isn't a one-size-fits-all process. There are several types, each involving different combinations of atomic orbitals. The most common are sp, sp2, and sp3 hybridization. Each type leads to a distinct molecular geometry and bonding pattern. For example, sp3 hybridization results in a tetrahedral shape, while sp2 gives a trigonal planar structure. Understanding these types is key to predicting how atoms will bond in different molecules. Start with sp3 hybridization, which involves the mixing of one s orbital and three p orbitals. This combination creates four equivalent sp3 hybrid orbitals, each pointing toward the corners of a tetrahedron. This arrangement is seen in methane CH4, where carbon forms four single bonds with hydrogen atoms. The tetrahedral geometry minimizes electron repulsion, making the molecule stable. sp3 hybridization is a cornerstone of organic chemistry, especially in alkanes. Next up is sp2 hybridization. Here, one s orbital mixes with two p orbitals, creating three sp2 hybrid orbitals and leaving one unhybridized p orbital. The three sp2 orbitals arrange themselves in a trigonal planar geometry, 120 degrees apart. This type of hybridization is found in molecules like ethene C2H4, where the unhybridized p orbital forms a pi bond, resulting in a double bond between carbons. sp2 hybridization is crucial for understanding alkenes. Finally, sp hybridization involves the mixing of one s and one p orbital, resulting in two sp hybrid orbitals. These orbitals align in a straight line, 180 degrees apart, giving a linear geometry. The remaining two p orbitals stay unhybridized and can form two pi bonds. This type of hybridization is seen in molecules like Ethyne C2H2, where a triple bond forms between the two carbon atoms. sp hybridization is key for understanding alkane. Visualizing hybrid orbitals can make the concept much clearer. Imagine the original atomic orbitals as different shapes, spherical for s, dumbbell shape for p. When they hybridize, these shapes blend to form new identical orbitals that point in specific directions. This visualization helps explain why molecules adopt certain geometries and why bond angles are what they are. It's a powerful tool for understanding molecular structure. Let's look at methane CH4 as a real-world example of sp3 hybridization. In methane, the carbon atom forms four single bonds with hydrogen atoms. The sp3 hybrid orbitals arrange themselves in a tetrahedral shape, with bond angles of about 109.5 degrees. This arrangement maximizes the distance between electron pairs, minimizing repulsion and making the molecule stable. Methane's structure is a textbook example of how hybridization determines molecular geometry. Ethene C2H4 showcases sp2 hybridization. Each carbon atom forms three sigma bonds using sp2 hybrid orbitals, while the remaining unhybridized p orbital on each carbon overlaps to form a pi bond. This results in a double bond between the carbons and a planar structure with 120-degree bond angles. Ethene's structure is a classic example of how hybridization explains the presence of double bonds and molecular shape. Ethyne C2H2, also known as acetylene, is a perfect example of sp hybridization. Each carbon atom uses sp hybrid orbitals to form two sigma bonds, one with another carbon and one with hydrogen. The two remaining unhybridized p orbitals on each carbon overlap to form two pi bonds, resulting in a triple bond between the carbons. The molecule is linear, with a bond angle of 180 degrees. Hybridization directly influences bond angles and molecular geometry. For instance, sp3 hybridization leads to a tetrahedral shape with 109.5-degree angles, sp2 gives a trigonal planar shape with 120 degrees, and sp results in a linear shape with 180 degrees. These geometries minimize electron repulsion, making molecules more stable. Understanding these relationships is key to predicting molecular shape. Hybridization also helps explain the formation of sigma and pi bonds. Sigma bonds are formed by the head-on overlap of hybrid orbitals, while pi bonds result from the side-on overlap of unhybridized p orbitals. Single bonds are always sigma bonds, while double and triple bonds include one sigma and one or two pi bonds. This distinction is crucial for understanding the strength and reactivity of different bonds. Carbon is the poster child for hybridization because it can form sp3, sp2, and sp hybrid orbitals. This versatility allows carbon to create a vast array of molecules, from simple alkanes to complex aromatic compounds. The ability of carbon to hybridize in different ways is the foundation of organic chemistry and the diversity of life itself. Carbon is the most famous. Other elements also undergo hybridization. Nitrogen, oxygen, and even some transition metals can hybridize their orbitals to form stable bonds. For example, nitrogen in ammonia NH3 uses sp3 hybridization, while oxygen in water H2O also adopts sp3 hybridization. This concept is not limited to organic molecules but is a general principle in chemistry. Let's take a closer look at ammonia NH3 and water H2O. In both molecules, the central atom uses sp3 hybridization. In ammonia, nitrogen forms 3 bonds and has 1 lone pair, resulting in a trigonal pyramidal shape. In water, oxygen forms 2 bonds and has 2 lone pairs, giving a bent shape. These geometries are direct results of sp3 hybridization and the presence of lone pairs. Lone pairs of electrons occupy more space than bonding pairs, which affects molecular geometry. For example, in water, the 2 lone pairs on oxygen push the hydrogen atoms closer together, resulting in a bent shape. In ammonia, 1 lone pair on nitrogen leads to a trigonal pyramidal shape. Hybridization helps explain these deviations from ideal geometries. Transition metals can also undergo hybridization, often involving d orbitals. For example, in coordination compounds, metals like iron or copper can use sp3d or sp3d² hybridization to form complex geometries such as trigonal bipyramidal or octahedral. This expands the range of possible molecular shapes and bonding patterns, making transition metal chemistry rich and diverse. sp3d hybridization, 1s3p and 1d orbital mix to form 5 equivalent orbitals, resulting in a trigonal bipyramidal geometry. In sp3d² hybridization, 1s3p and 2d orbitals combine to form 6 equivalent orbitals, giving an octahedral geometry. These types are common in transition metal complexes and help explain their unique structures. Hybridization is a powerful tool for predicting molecular shape. By knowing the type of hybridization, you can often determine the geometry of a molecule. For example, sp3 means tetrahedral, sp2 means trigonal planar, and sp means linear. This predictive power is invaluable for chemists designing new molecules or studying unknown compounds. Type of hybridization can also influence a molecule's reactivity. For instance, sp-hybridized carbons and alkanes are more electronegative and reactive than sp2 or sp3 carbons. This affects how molecules participate in chemical reactions, such as addition or substitution. Understanding hybridization helps chemists predict and control chemical behavior. A hybridization is a useful model. It has its limitations. It doesn't always accurately predict the properties of all molecules, especially those involving delocalized electrons or resonance structures. In such cases, more advanced theories like molecular orbital theory provide a better explanation. Still, hybridization remains a valuable tool for understanding many common molecules. Resonance structures occur when electrons are delocalized across multiple atoms, as seen in benzene. In such cases, hybridization helps explain the average geometry, but molecular orbital theory is needed for a complete picture. Benzene's carbons are sp2 hybridized, giving a planar structure, but the electrons are shared across the ring, creating extra stability. Aromatic compounds like benzene are a special case. All the carbon atoms in benzene are sp2 hybridized, forming a planar hexagonal ring. The unhybridized p orbitals overlap to create a delocalized pi system, which gives aromatic compounds their unique stability and reactivity. Hybridization is key to understanding the structure of these fascinating molecules. Hybridization isn't just important in chemistry labs, it's also crucial in biology. For example, the structure of DNA and proteins depends on the hybridization of carbon, nitrogen, and oxygen atoms. The shapes of these molecules determine their function, making hybridization a key concept in biochemistry and molecular biology. Hybridization affects many substances we encounter daily. From the carbon dioxide we exhale to the plastics we use, the shapes and properties of these molecules are determined by hybridization. Even the flavors and fragrances in food and perfumes are influenced by the hybridization of atoms in organic molecules. Materials science, hybridization explains the properties of substances like diamond and graphite. Diamond, with sp3 hybridized carbon atoms, forms a rigid three-dimensional network, making it extremely hard. Graphite with sp2 hybridized carbons forms layers that slide over each other, making it soft and slippery. These differences arise from the type of hybridization involved. Nanotechnology relies heavily on the principles of hybridization. Carbon nanotubes in graphene, for example, are made up of sp2 hybridized carbon atoms. Their unique properties, such as strength and conductivity, are direct results of their hybridized structures. This makes hybridization a foundational concept in cutting-edge technology. In pharmaceutical chemistry, understanding hybridization helps scientists design drugs that fit precisely into biological targets. The shape and reactivity of drug molecules depend on the hybridization of their atoms. This knowledge allows chemists to create more effective and selective medications. Hybridization also plays a role in environmental chemistry. The structure and reactivity of pollutants, greenhouse gases, and other environmental chemicals are influenced by the hybridization of their atoms. Understanding these structures helps scientists develop strategies for pollution control and environmental protection. Colors of many compounds, especially transition metal complexes, are influenced by the hybridization of their atoms. The arrangement of orbitals affects how molecules absorb and reflect light, leading to the vibrant colors seen in gemstones, dyes, and pigments. Hybridization is thus linked to the beauty of the material world. Ordination compounds, often involving transition metals, showcase complex hybridization patterns. Ligands bond to the central metal atom using hybrid orbitals, resulting in a variety of geometries like octahedral, square planar, and tetrahedral. Understanding hybridization is essential for predicting the structure and behavior of these compounds. Magnetic properties of molecules can also be traced back to hybridization. The arrangement of electrons in hybrid orbitals determines whether a molecule is paramagnetic or diamagnetic. This is especially important in transition metal complexes, where unpaired electrons in hybrid orbitals lead to interesting magnetic behaviors. Spectroscopic techniques such as infrared and nuclear magnetic resonance (NMR) rely on the hybridization of atoms to interpret molecular structures. The vibrations and energy transitions observed in spectra are influenced by the types of bonds and hybrid orbitals present. This makes hybridization a key concept in analytical chemistry. Energy required to form or break bonds is influenced by hybridization. For example, bonds involving sp hybridized atoms are generally stronger and shorter than those involving sp2 or sp3 atoms. This affects the stability and reactivity of molecules, making hybridization a key factor in chemical energetics. Molecular polarity is also affected by hybridization. The arrangement of hybrid orbitals determines the distribution of electrons and the overall dipole moment of a molecule. This, in turn, influences properties like solubility, boiling point, and intermolecular interactions. Type of hybridization in a molecule can influence the strength and type of intermolecular forces it experiences. For example, molecules with sp3 hybridized atoms may form stronger hydrogen bonds, while those with sp2 or sp hybridization may have different van der Waals interactions. These forces affect the physical properties of substances. Solubility is another property influenced by hybridization. The shape and polarity of molecules determined by their hybridization affect how well they dissolve in different solvents. For instance, polar molecules with certain hybridizations are more soluble in water, while nonpolar molecules dissolve better in organic solvents. Boiling point of a substance is related to the strength of its intermolecular forces, which are influenced by hybridization. Molecules with stronger hydrogen bonds or dipole-dipole interactions, often due to specific hybridizations, tend to have higher boiling points. This is an important consideration in both chemistry and industry. The acidity of a molecule can also be linked to hybridization. For example, hydrogen atoms attached to sp hybridized carbons are more acidic than those attached to sp2 or sp3 carbons. This is because sp hybridized atoms hold electrons closer, stabilizing the negative charge left behind after deprotonation. Isomerism, where molecules have the same formula but different structures, is often explained by hybridization. The type and arrangement of hybrid orbitals determine whether a molecule can exist as different isomers, such as cis-strands or structural isomers. This adds to the diversity of chemical compounds. In industrial chemistry, understanding hybridization is essential for designing catalysts, polymers, and other materials. The efficiency and selectivity of chemical processes often depend on the hybridization of atoms in the reactants and products. This knowledge drives innovation in manufacturing and technology. Let's recap what we've learned. Hybridization is the mixing of atomic orbitals to form new equivalent orbitals that explain molecular shapes and bonding. It's a versatile concept that applies to carbon, other main group elements, and even transition metals. Hybridization influences everything from molecular geometry to reactivity, color, and material properties. As chemistry advances, our understanding of hybridization continues to evolve. New computational methods and experimental techniques are revealing even more about how atoms bond and interact. Hybridization remains a foundational concept, bridging the gap between classical and modern chemistry, and will continue to shape scientific discovery for years to come.